A pleasant day to each and everyone. I am Mae H. Optina,
And I'm Zoel Anghelo Remolador.
and we are the Group 11. Today, we will be discussing two important topics, which covers first, photoelectrochemical energy conversion, and second, electrochemical energy conversion. But before we dive into them, let us take a quick recall of what energy conversion really means. So, energy conversion is the process of transforming one form of energy into another. In the context of sustainable energy systems, our goal is to convert renewable sources like sunlight or chemical energy into useful electricity or fuels. In this video, we will explore two advanced types of energy conversion which I have mentioned earlier. Both involve electrochemical reactions, but they differ in how the energy is supplied and transformed. And now, to begin our first topic, I will pass the floor to my partner, Zoel, who will explain what photoelectrochemical energy conversion is all about.
Photoelectrochemical, or PEC for short, energy conversion, refers to the process of using light energy, usually from the sun, to drive electrochemical reactions that produce chemical fuels. Unlike conventional photovoltaic systems that convert sunlight directly into electricity, PEC systems convert sunlight, or solar energy rather, into storable chemical energy. This process mimics the natural photosynthesis in plants, where sunlight is used to store energy in chemical bonds. The primary purpose of PEC systems is to create a clean, sustainable, and carbon-free method of fuel generation. By combining the principles of solar energy harvesting and electrochemistry, PEC devices offer a promising path toward renewable hydrogen production and other solar-driven chemical reactions. Now that we've outlined the purpose of electrochemical energy conversion, let's move on to the basic principles and mechanisms that allow PEC systems to operate. Firstly, we have photoexcitation. When sunlight strikes the surface of a semiconductor material, photons with energy equal to or greater than the semiconductor's band gap excite electrons from the valence band to the conduction band. This process generates electron-hole pairs, providing the charge carriers necessary for the reaction. The excited electrons and the remaining holes then move in opposite directions under the influence of an internal electric field or an external bias. Finally, at the semiconductor electrolyte interface, the photo-generated charges drive redox reactions. In a typical water-splitting PEC system, oxidation occurs at the anode, producing oxygen, while reduction at the cathode produces hydrogen. This converts solar energy into chemical bonds stored in molecular hydrogen, forming a renewable fuel. Understanding these mechanisms gives us the foundation to explore the components of a PEC cell, which work together to carry out these processes. First, we have the photoanode. The photoanode is a light-absorbing semiconductor that initiates the process by absorbing photons. The absorbed light excites electrons, which then participate in oxidation and reduction reactions, most notably the splitting of water into hydrogen and oxygen. Common photoanode materials include titanium dioxide, hematite, and tungsten trioxide for their stability and availability. On the other side of the cell, we have the counterelectrode. The counterelectrode, or cathode, completes the circuit and supports the complementary reduction reaction, often converting hydrogen ions into hydrogen gas. Materials like platinum, nickel, and carbon are commonly used for their high conductivity and catalytic efficiency. The electrolyte provides the medium for ion transport between electrodes. It typically consists of water or an aqueous solution containing ions that support charge balance and reaction continuity. Its composition and pH significantly affect efficiency and durability. After examining the key components, we can now look at emerging chemical applications that make photoelectrochemical technology increasingly relevant and innovative. Recent research expands PEC energy conversion beyond water splitting to produce a diverse range of valuable chemicals and fuels. These emerging applications showcase the potential of PEC systems not only for renewable hydrogen production but also for sustainable chemical manufacturing, carbon utilization, and pollution reduction. Water splitting remains the most developed PEC process, where sunlight drives the separation of water into hydrogen and oxygen. Hydrogen serves as a high energy density fuel and chemical feedstock for industrial synthesis, including ammonia and methanol production. PEC production offers a sustainable alternative to the energy intensive chlor-alkali process, which accounts for about 1% of global electricity use. By replacing oxygen evolution with chlorine evolution at the photoanode, hydrogen and chlorine can be co-produced using abundant seawater as the electrolyte. PEC nitrogen reduction offers a low temperature, low pressure alternative to ammonia synthesis using sunlight and water instead of fossil fuels. PEC systems can synthesize hydrogen peroxide through selective oxygen reduction and water oxidation under solar illumination. Lastly, PEC carbon sequestration involves converting captured carbon dioxide into carbon-based fuels like methanol, ethanol, or methane. PEC systems still face barriers to large-scale implementation, however, including low solar-to-hydrogen efficiency and electrodegradation. Current research focuses on developing stable and low-cost photoelectrodes, understanding charge transfer dynamics, and using AI for material design to accelerate progress toward carbon neutrality goals. With these emerging applications in mind, let us now widen our view to the broader applications of PEC energy conversion in real-world systems. Hydrogen fuel generation, the most established and widely studied application of PEC systems, as mentioned earlier, is solar water splitting for hydrogen production. In this process, sunlight drives the separation of water molecules into hydrogen and oxygen. The resulting hydrogen gas serves as a clean, renewable, and storable energy carrier that can be used in fuel cells, transportation, and various industrial processes. This application provides a sustainable alternative to hydrogen production methods that rely on fossil fuels. Next, we have carbon dioxide reduction. Again, as mentioned earlier, PEC devices can convert captured carbon dioxide into valuable chemicals such as methanol, formic acid, and hydrocarbons through photocatalytic reduction. This process not only reduces atmospheric carbon dioxide levels, but also produces synthetic fuels and industrial feedstocks, contributing to a circular carbon economy. Research continues to improve selectivity and efficiency through advanced catalyst and multi-component semiconductor systems. Lastly, we have pollutant degradation and wastewater treatment. PEC systems are also used in environmental remediation, particularly in breaking down organic pollutants and hazardous compounds in wastewater. When illuminated, the semiconductor materials in the PEC cell generate reactive oxygen species that can oxidize and decompose pollutants. This process allows for simultaneous solar energy utilization and pollutant removal, making PEC systems valuable for sustainable treatment. Of course, any technology comes with strengths and limitations. Its main advantages are direct solar to fuel conversion, clean and renewable hydrogen production, low operating temperatures, carbon dioxide utilization capability, simple system architecture, integration with other renewable systems, environmental co-benefits, and long-term energy storage through chemical fuels. While some of its disadvantages are low solar to hydrogen efficiency, material stability issues, high cost of advanced materials, limited visible light absorption, competition with side reactions, scalability challenges, and electrolyte management and safety concerns. This concludes our discussion on photoelectrochemical energy conversion. At this point, I will pass the floor to April, who will continue with electrochemical energy conversion.
Have you ever wondered how a battery can power your phone or how electric cars can run without fuel? That's right. That's because of this amazing process called electrochemical energy conversion, the clean and efficient way of turning chemical energy into electrical energy. Now, let us define what electrochemical energy conversion is all about. Electrochemical energy conversion refers to the process of transforming chemical energy directly into electrical energy or vice versa through oxidation reduction or redox reactions that occur in electrochemical cells. This process is fundamental to modern energy systems as it allows for clean, efficient, and direct energy transformation without combustion. Common devices that utilize this process include batteries, fuel cells, and electrolyzers. In short, electrochemical energy conversion happens when oxidation and reduction reactions interact to produce electricity. So how does it actually works? If you remember from chemistry, an electrochemical system has two electrodes, an anode where oxidation occurs and electrons are released, and a cathode where reduction happens and electrons are accepted. These two electrodes are placed in an electrolyte that allows ions to move. While ions move inside the cell, electron flows through an external circuit, and that flow is what creates usable electric current. Depending on the device, this process can either release energy, like in batteries and fuel cells, or consume energy, like in electrolyzers. For example, in a hydrogen fuel cell, the overall reaction is two molecules of hydrogen combined with one molecule of oxygen to form two molecules of water while releasing electricity and heat. For at the anode part, hydrogen is oxidized into protons and electrons, while at the cathode part, oxygen is reduced to form water. So as long as fuel is supplied, the system generates electricity continuously. Now let us move on to the types of electrochemical systems. There are three major types of electrochemical systems. First, fuel cells. Fuel cells are devices that convert the chemical energy of a fuel, such as hydrogen, directly into electricity through redox reactions. Fuel cells operate continuously as long as fuel and oxidant are supplied. Second, batteries. These are electrochemical systems that store energy in chemical form and release it as electrical energy when needed. They can be rechargeable, like lithium ion, or non rechargeable, like alkaline cells. And lastly, electrolyzers, systems that use electricity to drive non spontaneous reactions, such as the electrolysis of water to produce hydrogen and oxygen gases. They play a key role in hydrogen energy production and storage technologies. We have here also its applications. These systems are used in many areas, including electric vehicles and hybrid transportation systems like fuel cells and batteries. Also, in portable electronic devices such as laptops, smartphones, and tablets. It can be also used in renewable energy storage like battery banks for solar and wind systems. Furthermore, it can be also used in industrial hydrogen production or electrolyzers, and lastly, it can be served as backup and grid energy storage systems. And some of its advantages include high energy conversion efficiency, environmentally friendly, quiet and reliable operation, and scalable for different applications. However, these technologies also have limitations, as it can be high cost of materials, hydrogen storage and distribution challenges, limited lifespan of some electrochemical systems, and performance degradation over time. So, That's how electrochemical energy conversion works and why it is important in many modern technologies. To sum it all up, electrochemical energy conversion shows how simple chemical reactions can power devices cleanly, efficiently, and sustainably. And that covers the fundamentals, how it works, its types, and its real world applications. So that ends our presentation. We hope you have learned something and thank you for watching.